Good evening. Welcome to People's University Livestream. This is the finale of our series on physical science. We'll probably. Good evening. Welcome to People's University Livestream. This is the finale of our series on physical science. I know what the problem is. Hold on.
Okay.
Good evening. Welcome to People's University Livestream. I had a window open. I'm sorry about that. With so I could see, so I could monitor and how things looked, and then I forgot that I had the window open. Let me start again. Welcome to People's University Livestream, and this is the finale of our science series. And I'm sure that we'll do more science in the future, but this has been, I think, a very well-received and fun program. Before we introduce our guest for the finale, I will make just a few announcements. This Tuesday, February 23rd at noon, we'll have our second Ann Thomas Memorial Lecture. And the guest this year is Crystal Wilkinson, who is a very fine writer from the University of Kentucky, where she teaches in the creative writing program. And if you haven't read her work, such as Blackberries, she is just a beautiful writer. That will be Tuesday at noon. Tonight, if you ask a question, make a comment, you will have a chance. I must tell you, we have the Marie Curie tumbler back up for grabs because David Wren took the Great Beards of Science. I gave him the option. I gave him door number 2, and he took it. So you can win the Marie Curie tumbler tonight by asking a question, and you'll get into the drawing. Okay, let us begin. Stacey Kefalos Vargas is a professor at Virginia Military Institute in Lexington, Virginia. She received her BS in physics from Wheeling College in what year did we graduate, Stacey? 1988. Wow. Yeah. She's a classmate of mine, and her Masters and Ph.D. in physics from the University of Connecticut. She joined the faculty in the Department of Physics and Astronomy at VMI in 1996. She was the first woman in science and engineering at VMI to receive tenure and promotion to full professor. She is the recipient of a VMI Distinguish Teaching Award and the Thomas Jefferson Teaching Award. In addition to teaching a variety of physics courses, she performs research in laser spectroscopy, free space optics, and visible light communications. You'll hear more about that tonight. She's published many articles and received several grants to fund her research. She has collaborated with companies in pursuing novel wireless communication technologies. In 2017, she won the Innovation in Higher Education Award from the Shenandoah Valley Technology Council for her novel research using ultra-short pulse lasers in free space optics communication. She is passionate about her teaching and her research, and she resides in Lexington, Virginia with her husband, Albert. Hi, Albert. And her 5 children.
He'll be there.
And here is Stacey. Take it away.
Okay, thanks, Sean. I'm going to try to share my screen this time and make sure it works. So let's see if this goes. Share. Okay. All right, so let me get my slideshow started from the beginning. And hopefully, let me hide this. Hopefully you can see the screen now. So I'm going to talk about light, lasers, and free space optics. So you might know a little bit about light, but I don't know if you've ever thought about light and its behavior. If not, that's what we're going to do tonight. And I have to be honest, there's a slight twist to how I'm presenting it because I want you to learn enough to explain how a laser works by the end of it. So we're going to start where we sort of left off the last lecture. If you were here, we talked about Newton and classical mechanics. And so in talking about the nature of light and how light behaves, we start back in the 17th century with Newton. He devised a way to describe light as a particle. And he was able to prove things like how reflection and refraction and other properties of light work with his particle theory. At the same time that Newton was talking about the particle theory, there was another scientist talking about wave theory. And this is a new character. We haven't met Christian Huygens, so we didn't meet him last time around, but he had a competing theory with Newton, and he thought that light was a wave. And if you look down here, he sort of thought you had these wave fronts, and on the wave fronts, they always started a new set of these little wavelets, these little smaller arcs that created a whole new wavefront. So with this sort of idea, Huygens was able to explain everything that Newton could explain with his particle theory, but Huygens did it with the wave theory. However, in the 17th century, because Newton was so important and leading the way in science, particle theory really prevailed throughout the 17th century. It wasn't until about 1801, when we have this famous experiment called Young's double slit experiment. And so really, to talk about the nature of light, there's a couple of experiments along the way that really formed our decision of how we treat light. And this was a major one in thinking about light as a wave. And in Young's double slit experiment, he was able to demonstrate the interference of light. And so before I talk about the experiment, I just want to remind you, if you know a little bit about interference, and interference they knew at the time was a wave phenomena. So water waves, sound waves, all these waves they already knew about behave in ways that we can study interference. And so if I look at the picture here, I don't know if I can draw with my pen, if I take two waves that I have up here and I add them together, and I add them so that their peaks are lined up everywhere. So if I take these two waves and I add them up with their peaks together, if they happen to be waves of exactly the same amplitude, maybe their height is 2 and this one's 2, and I add them together, then what I end up with down here is a wave that's double that amplitude, so 4. So it's much bigger. So we call that constructive interference. The two waves come together to form a bigger wave. If instead I bring those two waves together where the peak and a not peak, we'd call that a trough in physics. So instead of the peak, I have a trough lining up, and up here where I have a low, I have a high below. These two waves would be what we call out of phase. And as a result, when I add them together, I basically cancel them out. Many people have sound canceling headphones, so you're sort of familiar with canceling waves out. And that's exactly what happens when we do canceling out of waves. So it happens in all waves. We're going to talk about it now with light waves. So in Young's experiment, basically what he did, he had to use sunlight. So he took a light source and he shined it through a single slit just to create some coherence to that light. But what really mattered was that then he shines the light through two double slits. And so you might think about, oh, if I shine light through two double slits, I just get light on the other side. Well, in fact, you don't just get light on the other side. What happens is you get these sort of bright spots and dark spots of light on the other side. And so if I think about that in terms of the interference, what's happening here is when the two waves through each of those slits over there come through, they're lined up, sorry, my drawing's not great, with peaks together. If I look here where there's actually no light, what's happening there is a peak and a trough are lining up. And so I literally get places with spots. So if you could do this, if I was with you, I'd get a laser diode, shine it through two double slits. I could actually demonstrate this really well. Oops. So what happens is you get bright spots, no light, bright spots, no light. And that was all due to the fact that as the light went through the two slits, it was interfering. And that really demonstrated the fact that light was a wave. And so Young's double slit is sort of in science a groundbreaker showing light behaves as a wave because it interferes in this experiment. Maxwell, we already talked about him a little bit last time as well, so he's a familiar face to you now. He talked and studied about electromagnetic radiation, and he treated electromagnetic radiation as a wave. And when he was studying his electromagnetic radiation, if you remember last time, we said that he found out that the speed of his electromagnetic waves was equivalent to the speed of light, this C over here on the side, 3 times 10 to the 8th meters per second. And he realized that if his electromagnetic radiation had the same speed as the speed of light, and it was a wave, then the light had to be an electromagnetic wave. And so this sort of solidified the Young's double slit idea that light was a wave. Not only is it a wave, it's an electromagnetic wave, according to Maxwell's theory. So we had particle by Newton. Now we've got some solid wave theory. So we think of light as a wave, according to Maxwell and Young. Okay, then in the 1900s, so we've gone from the 1700s, 1800s, now we're in the 1900s. In the 1900s, there was someone called Planck, Max Planck, and he explained that when light is interacting or light is released from matter or absorbed by matter, that it had to be done in these sort of discrete amounts of energy. So he was basically studying something called black body radiation. So he was heating solids until they glowed, I guess is how I'll describe that. And when he did this, he found that you couldn't just have sort of electromagnetic radiation released. You had to have this set amount of electromagnetic radiation. And so we say the energy is in sort of integer multiples of this value. And don't worry about the value. It's just a set value. It depends on the frequency of the light. And you might call that frequency the color of the light. Darn. And H is a constant. And so what he found in his study was that when he heated these bodies up, that it had to be this set amount of radiation that was either absorbed or released from those black bodies. So this started to indicate again that electromagnetic radiation had a particle nature or some kind of quantized energy associated with it. And so another black body radiation was one. This now photoelectric effect is another experiment that was sort of groundbreaking in our study and understanding of light and how it behaves. And in this case, we look at light. Hertz was the first to observe this. He looked at light, and light was hitting sort of a surface over here. This is a metal surface over here. He looked at the light hitting that surface, and what he found was when light hit the surface, electrons were released from the surface. So he hit light, and then all these electrons were released. And he could see that because he had it set up in a circuit and he had measuring current, but that's not all important. All that matters to us right now is that light hits this material, this metal emitter plate, and it starts emitting electrons. So something was going on with the interaction of the light, the metal, to release the electrons. It wasn't until later on in 1905, Einstein was able to explain the photoelectric effect that Hertz observed using Planck's theory. So they sort of all come together nicely in the way Einstein was able to describe how light behaves when it's interacting with matter in the photoelectric effect. And so in the photoelectric effect, the Einstein's interpretation, he treats these light waves as they're coming in here as these quanta of light that we now call photons. So these are now going to be photons or particles of light. And they have energy, as Planck described it, as H times nu. H being that constant, we call Planck's constant, and nu is the frequency of the light. Okay, so each particle of light comes in, interacts with an electron, and an electron is released. So Einstein sort of gave this quantization to the light, made it sort of a particle that we now call photons, and said that it had to have this set amount of energy to release the electrons from the surface. And so this was really groundbreaking and taking us back to where we started with Newton, that light wasn't a wave here, light was acting like a particle. And not only was it acting like a particle, there was a certain amount of energy it had to have to release electrons from the surface in experiments like the photoelectric effect. And to further that and make it, even more emphasis on it, when Bohr developed his idea of the hydrogen atom, he said something similar where essentially you had this nucleus and then you have these orbitals or these energy levels, I like to call them energy levels, where electrons can be. And in order for an electron to go from one energy level to another, so if it's out here in this third energy level and wants to go down to the second energy level, it has to release energy. So if the electron transitions from one energy level to another, it has to release energy. That energy is the difference between those two levels. So if we knew the level of energy 1 here and energy 2, we could subtract them. And that would tell us exactly what kind of photon would be released here, because it have to be equal to H, the constant, times the frequency. And so we can, based on those energy levels, figure out what type of energy was released. And in the same way, if you wanted to take an electron from sort of this N2 and up to N3, you'd have to absorb a photon. So this energy had to be released or absorbed in order for the transition to take place. And it had to be that set energy of the photon. Okay, so let's sort of take this in one more step, because we're going to need this when we talk about lasers. So this is all light interacting with matter, starting with the photoelectric effect, talking about Bohr, and so Bohr's atom. And so let's emphasize this a little more. So if I look at these energy levels, instead of drawing Bohr's circles, right, I can draw them instead of circles, I can draw them as just energy levels. So I have energy level 1 and energy level 2. If I subtract those two energy levels, E2 minus E1, then I know the energy of the photon that has to come in here to make an electron in E1 go up to E2. So it's that set amount of energy. The difference in those two energy levels has to be equivalent to the energy of the photon that comes in. So basically, it has the energy to move those up. And in the same way, if I want the photon to be electron to drop down, so if I want to take an electron in E2 and drop it to E1, then that same amount of energy, that E2 minus E1, has to be released as a photon. So we can absorb the photon or we can emit the photon. And so we refer to this as absorption, where we bring a photon in and take an electron up to a higher state. Or we refer to it as emission if the electron's in the higher state and then drops down to the ground level. And in each case, there's either a photon absorbed with that equivalent energy or a photon released with that equivalent energy. And so this is sort of how we think about photons and their interaction, light interacting with matter in terms of absorption and emission, and all sort of built upon these scientific experiments that we've discussed. And so that was all good in emphasizing particle theory and how light interacts with matter being a particle. Then later on in the 1900s, this guy, another new character for you, de Broglie or de Broglie, depending on how you pronounce it, decided to study the photoelectric effect in sort of a reversed psychology. And this relates back to a question somebody asked in the last lecture about electrons. And so what de Broglie did was he said, well, if people can look at the light waves, and treat them as particles, then can we take a particle and treat it as a wave? So can I take the electron and give it a wave nature? And that is exactly what he came up with in what we call now the de Broglie wavelength. And so you can take any sort of matter that has a velocity, and you take Planck's constant and you divide it by that mass and velocity, and you can figure out the wavelength of that particle. So all particles can also have a wave nature. So we went from particles to wave to now we're back to particles having wave nature. So where do we settle in science for the theory of light? Well, where we settle is what we call wave-particle duality of light. And so we say when light interacts with matter, we treat light as a particle. So thinking of things like the photoelectric effect, those are all cases where we treat light as a particle, as a photon. But when light is doing things like interfering, diffraction, or just its propagation through space, we often think of it just as a wave. So we don't have to call it a particle or a wave. We can actually call it both. And maybe that sounds like a bit of a scapegoat, but it works. And the science around it all works. And there's a great quote by Einstein. I don't know the exact quote, but it basically says that everyone thinks they know what light is. I spent my entire life trying to figure out what a photon was, and I still don't understand it. So if you're still confused by light, you're in good company with Einstein, and just settle in with the fact that we call it a wave, we call it a particle, depending on what allows us to describe the interaction of matter or propagation of light. All right. So now that I've sort of given you some foundation in light in general, I want to talk more about an application of light, and that is lasers. And you may already know this, but laser is actually an acronym. Laser stands for Light Amplification by Stimulated Emission of Radiation. So it's an acronym for all of that. And what's really important to us right here is the amplification, obviously, but the stimulated emission is really key to what makes the laser work. And so we need to talk about stimulated emission a little bit to understand more about the laser. I should mention, before the laser, there was something developed called the maser, and that stood for microwave amplification by stimulated emission. So this stimulated emission can be used in different types of radiation, not just light. We can use it with microwaves as well, but we use lasers, and that's what we're going to talk about. Theodore Maiman was the first to build a laser in the 1960s. So even though the idea of stimulated emission was around since 1905, 1917, I guess, with Einstein, took a while to actually put it into place. So what is stimulated emission? Well, we already talked about absorption. We said absorption is if I put light, a photon energy into this atom, and the electron can transition up to a higher state. And emission occurs if I am in an excited state already and the electron drops down, then it emits a photon. So what is stimulated emission? So stimulated emission was developed, the theory of it, by Einstein. And he basically said, if you have an electron that's already in this excited state, and you bring a photon that has the exact energy that you need, remember that energy is just the difference between these two energy levels. If you bring a photon in that has that exact energy match, it can stimulate this electron to drop down. And when that electron drops down, it releases a second photon. And it doesn't just release a photon, it releases an identical photon. And that identical is really key to understanding stimulated emission, how important it is to how a laser works. Because you basically get two photons for the price of one, and those photons are identical. Their peaks are going to line up. Remember that constructive interference? Their peaks are going to line up perfectly. They're going to travel in the same direction. They're going to all have the same wavelength, and they're going to stay in phase. And this is really key to what makes stimulated emission allow us to have a laser, is these identical photons that we can force out through stimulated emission. So let's take this and put it in a laser. So just in more technical terms, if you're talking about laser light, we say it's monochromatic, meaning it's one color, one wavelength, one frequency. It's highly directional, so we can force it in one direction. And it's coherent, meaning those phases, those peaks line up everywhere. And just to sort of give you an idea, to think about this more clearly, if you think about just an incandescent light, you might think about light of all different wavelengths traveling in all directions from the bulb, different wavelengths, different frequencies, as opposed to a laser where you'd see this sort of well-behaved light traveling in phase in one direction, all the same amplitudes, everything's identical. And so that's a really key difference between what we call regular light or incoherent light and laser light, which is very coherent. Okay, so what are the parts of the laser and how do we get this stimulated emission to occur? There's really these few main parts to a sort of a generic laser system. There's the pumping source, which is here. So you've got a pumping source up here. And it's going to be responsible for creating getting the electrons into the excited state and getting them ready for stimulated emission. Then you're going to have a gain medium. And most lasers are named after their gain medium. So if you've ever heard the name of a laser, maybe a helium neon laser or a CO2 laser, that is referring to what's in this gain medium. What material is in here that allows us to have the stimulated emission? So this is where stimulated emission takes place. And the laser name is telling you what's in that gain medium. And it can be a solid, it can be a liquid, it can be a gas, it can actually be fiber optic or diode. So there's a variety of types of gain mediums that you can have. The first laser that Maiman built was actually a solid, it was ruby. So this was a ruby crystal in here. Many lasers are just crystals of some sort, if they're a solid state laser or solid material. But you can also have gas or other things. But the pumping source is responsible to get the electrons in the gain medium into excited state. Then I have a mirror here that fully reflects the light and a mirror here that partially reflects the light. So I'm kind of setting up an optical amplifier, allowing the light to sort of reflect back and forth. It never gets out on this side, but some of the laser light will be released on this side. And so let's look a little more detail at each of these parts. So again, the point of the pumping source is this. If I look at a normal setup inside that gain medium, the electrons aren't going to be in the excited state. The electrons are going to be happy here in the ground state. they're not going to go to the excited state unless we force them up there. There's different types of pumping sources. You can do it optically, electrically, or through a gas, but let's just think of it optically. So if I think about it over here, if I bring in photons, right, that have the right energy, they can take all these electrons and they can bring them up to an excited state. And that's exactly what a pumping source does in the laser system. It just continuously adds energy so that you always have an infinite number of electrons in this upper state. We call this population inversion. So instead of having these electrons all sitting here in the ground, they're all sitting here at the top. And so as a result, I've always got electrons in here allowing for stimulated emission. And so that's the purpose of the pumping source. So then if we look at that inside the gain medium, so in my gain medium down here, this whole white piece is my gain medium. Now in my gain medium, I've got all these electrons that are just sitting here waiting for stimulated emission to occur. So if I bring in a photon that's the exact energy, it's going to knock an electron down. Then I'm going to have 2 photons coming here, and then 3, and then 4, and I keep amplifying the number of photons through the stimulated emission. These photons all get to here. Some of the light's released, but some of it also goes back. And so some of the photons create stimulated emission, hit the reflector, and they keep going back and forth, constantly creating stimulated emission. The pumping source has an infinite source of electrons up here. So this process can happen over and over and over. And there is, in fact, how we get our light out. And again, crucial to all this is that these photons are all identical, all traveling in the same direction, all the same frequency, all the same wavelength, and very coherent or in phase, so their peaks are all lining up. And so that's really the basics of how a laser works. If you can understand the stimulated emission, then you can really understand sort of the fundamental of how the laser works. I should mention there's sort of 2 types of lasers that we talk about. There are continuous wave lasers and there are pulse lasers. In a continuous wave laser, you can kind of think about like when you turn a flashlight on and the light just comes out and it just keeps coming out of the flashlight. A continuous wave laser is similar. We turn it on and light just comes out of that system. In a pulse laser system, you get sort of bursts of energy. So instead of having just a continuous wave of light, there's a bunch of these pulses that contribute to that light. You don't see them. The pulse and the frequency of the pulses is usually too fast. But within that, we can also build up the energy. So your pulse laser systems tend to have a little higher energy, and they're more precise in them. So a lot of your medical lasers are pulse laser systems because you've got these small pulses or bursts of energy that you can sort of concentrate down to a small area. And again, you can see this is an example of a ND-YAG laser, green laser. It's a super directional. It's a little bit of beam going in the lab. So let's talk a little bit about, now that you have an understanding of sort of what light is, what a laser is, what can we do with a laser? So I've done some different projects, but I thought I would talk about 2 of my most recent projects and how I've used lasers. And so one of the projects that I worked on for about 5 years, starting in, I don't know, about 2013 maybe, was what we call an ultra short pulse laser research project. And this was what we call free space optics. And in free space optics, it's exactly what it sounds like. You're basically sending light through free space. In our case, laser light through free space. And we were doing it to create a telecommunication link. So we literally wanted to put data on our laser and send it through free space. And study sort of the behavior of our signal and how it was able to penetrate through the atmosphere. Free space optics is a line of sight technology. So you have to be able to, if you're transmitting from one location, you have to be able to see the other location. So it's not, you can't have things blocking your beam. So you literally have to have a direct line of sight between where you're transmitting and where you're receiving. And this is actually a picture from a setup that we used originally in the project where we were testing our system. We sort of stole a little area of the press box this is the VMI football field. And we were in the press box aiming over here at the physics building. So we had a little window here in the physics lab. And so we could see each other, and that tree almost got in our way, but we were able to see around it. So free space optics, can allow us to transmit data through space on our laser. It's useful in places where maybe you don't want to have to lay fiber, it's too expensive, or you can't get to the ground to lay the fiber. Can be useful in, say, ground to satellite. It's also got some interest through backhaul, where we send information between cell towers. And when I was working on this project, this was a project that was funded from Center for Innovative Technology and through some VMI funding as well. But it was also a collaborative effort with a startup company that was hoping to build this as a technology that they could sell. And so the idea behind this project was really crucial, was the ultra short pulse laser. And so let me just talk a little bit about that laser system before I talk about the full project. So an ultra short pulse laser, and the one that we were using, again, it's one of those pulse laser systems. So you imagine these pulses that are emitted by the laser. And in our case, these pulses, the width of the pulse in time was 150 femtoseconds. And a femtosecond is 10 to the minus 15 seconds. And I don't know how else to tell you that. It's a 1/4 of a second. So each of these pulses is 1/4 of a second. And you would have to take 1 billion times 1 million femtoseconds to get a second. So these are really, really, really small pulses that come out of this laser system. And the idea was that these small pulses might penetrate the atmosphere better than, say, a continuous wave laser, because there is already some free space optics available with continuous wave lasers. So we were looking at it more from, can this ultra short pulse laser system do better? The repetition rate, so how often were we sending these pulses through free space? The repetition rate of our laser was 1.25 gigahertz. So a gigahertz means we were sending 1 billion pulses per second. So that was our rate of the laser. Later we'll talk about that as our data rate. So that also was how fast we could send our data through space. We were using a wavelength which was 1550 nanometers. The reason we chose that wavelength is because telecom, a lot of your telecom waves are all 1550 nanometers. So it was a very practical if we transition to from free space to fiber. And so if you're familiar with the spectrum, just to give you an idea, the visible spectrum, which is right in here, these are X-rays. And then we have the visible spectrum here. Visible goes from like 400 to 700 nanometers. So we were outside the visible over here in the infrared. So we couldn't see our laser beam at all, which could be kind of interesting when you're trying to line things up. So we couldn't see it, but we could tell by the power if we were in line. So that's a little bit about the laser system, very unique, these ultra short pulse laser systems. So what do we need to set up our link? So basically, to set up a free space optics link or any telecommunication link, really, you need your data. You have to put your data into some way, some sort of transmitter circuitry, and this can be pretty complicated. And you modulate your data in this transmitted circuitry. In our case, we had to modulate the data onto the laser beam. And then once we had the data on the beam, we send it through free space. So we send our laser here, but in addition to our laser, there's a bunch of data on it, get it to the receiver, and we recover the data out, and then we send it to here. So that data could be voice, it could be music, it could be anything. In our case, we just did a bunch of ones and zeros, random patterns of ones and zeros, because all digital signal, digital data that you send is really made up of ones and zeros. So if we could send a bunch of ones and zeros and get those same patterns of ones and zeros to the other side, then our link could work. And of course, you had to do it with long patterns. I couldn't just do 1 0 1 0. It had to be these sort of pseudo-random patterns. But in general, that's what you need to make a link. The distance that we wanted to use, we wanted to be greater than 1 kilometer, because in industry, to do something like backhaul between towers, if you want to make this a marketable product, you wanted to be a little greater than 1 kilometer to be able to do that. So our distance we set up was 1.25 kilometers. And then our data rate was driven by the rate of the laser, which was the 1.25 gigahertz. But that meant our data rate, we could send our data at 1.25 gigabits per second. So how do we do this? So we had to find a place to transmit, and we had to find a place to receive. So we had a really good transmitter station. None of our equipment was really ready for outdoors, so we had to do everything indoors. So on the top of our biology building, there was a window here in the greenhouse that we borrowed. So this is really a greenhouse for the biology department, and we set up our transmitter station in that part of the greenhouse. So we were at the top of our biology building in the greenhouse. And so this is the setup for our transmitter. This is the laser system. I know it doesn't really look like much except for a metal box. And we also had a way to modulate our data within this box. We designed it all and sort of had it all sort of manufactured into one box. So you can't really see much, but there's a laser in there. And then I'm taking my ones and zeros from this bit error rate tester, putting them onto the laser internally through connections. And then this yellow fiber is basically a fiber optic cable, which takes the laser with the data on it, sends it up here to this telescope, and then we transmit it out to our receiver. So the laser is connected with the fiber to the transmitter, and this telescope basically sends it out to the other side. And this is just a little viewing telescope that allows us to try to look to see if we're aligned. And then this over here is just our station where we're sort of monitoring everything. And one of the things that we really wanted to monitor were the weather conditions during the transmission of the data, because that's what impacts whether your data gets to the other side or not in most cases. So if you look out this window here, you can see that we have a bunch of weather station stuff out here. So let's take a look at that. So out on the roof outside of this, we built a full weather station. So not only were we sending data, we were analyzing weather data. And so to do that, we connected everything to a computer inside. So there's different weather devices here. This is called a precipitation monitor. So when rain or snow or anything falls in between, there's a laser here and a detector over here. And so when the rain falls through there, I can tell what type of precipitation it is, can tell the millimeters per second or millimeters per hour of the rate at which the rain is falling, or hail, whatever it happens to be. We can characterize what type of hail it is. It can do just about anything with precipitation. This is a visibility meter. Again, there's a laser and detector. And so as the visibility changes, it tells us through a computer connection what the visibility is. As you can see here, there's a lot of great fog. We wanted bad weather because we wanted to study this system in bad weather. And so this was a great day for us, a foggy day. Over here is a Davis weather station that allows to monitor all kind of weather conditions, just like temperature and humidity and those types of things. And then this was a fog monitor. So it basically sucks in the fog, and then it can tell you like the particle size and how many particles it brought in. When we borrowed this from a company, atmospheric research. They said every once in a while, a bird gets sucked into there and you'd have to pull it out. Fortunately, that never happened to us. I had warned the cadets if a bird got stuck in there, I was not pulling the bird out of the fog monitor. So then we go back. So from our window, we tried to see a place where we could, so from here, right, we had to have a line of sight from here to something we could see to be able to transmit to. And so in our case, what we could see out of the window was the hospital, which was 1.25, happened to be exactly 1.25 kilometers away. And so we needed a receiving station on the roof of that hospital. So while the chemists of the world are out there doing great things and making the world a better place for us, so drugs and everything else, physicists are trying to find a way to buy a toll booth and put it on a roof. So we're not quite where the chemists maybe are at this point in time. But anyway, we found a way to get a crane to come and take this toll booth that we bought and put it on the roof here. So we put it on the roof and we strapped it down tight as we could to this part of the building and hoped that it would hold in all kind of weather and keep our equipment dry inside. And sure enough, it did. But I have to confess that being in a metal booth on a roof in the middle of an electrical storm, hoping that your data is coming through free space, probably not the smartest thing to do for the sake of science. Okay, so inside that booth, we had this whole receiver station. And so the same way we had a telescope on the other side, we had a telescope on this side that could collect the beam coming at us. This is a view through the telescope right here. So if I look through that telescope, I can kind of see the greenhouse on the other side. And so that's what we were sort of looking for. We initially line up, and then we would have to look at our power meter and adjust things as we were watching the power. And then, as I mentioned, there's a lot of electronics that go into receiving the signal and bringing it off the laser. So there's another fiber optic that connects our signal that we receive back to our receiver circuitry. And then we can see that on the screen. We can monitor the data. We can see, okay, if we send a bunch of 1s and 0 pattern, did we get it back to the other side? And we can analyze our signal that way. Okay, oops, back up one. Okay, so what did we find out? We found out that we were able to transmit data over the distance of the 1.25 kilometers. We were able to send data, receive the data. All the data we sent got to the other side without a problem in most conditions. We even got through some really horrible rainstorms, torrential rain that we got collected from our weather data. So it worked very well, the ultra short pulse laser, in a variety of weather conditions. Fog is a problem. So in cases when we had days like this, as soon as the fog got to a certain density, we basically would lose our signal. As soon as the fog would start to lift, we'd get it right back. So it didn't affect our alignment any. It just totally disrupted the signal. It couldn't penetrate. The ultra short pulse laser at 1550 nanometers could not penetrate heavy fog. And then sunlight actually has some odd effects also at times on the alignment. But if you get a bigger telescope, then that you can eliminate that as a problem. And so we were very successful in proving that this could be a viable technology and does perform. We did some comparisons between the ultra short pulse and a commercial CW laser system that works in free space optics and definitely could perform better. So this was a very successful project. I'll just mention a little bit about one other project that we're currently working on. And this is a visible light communication project. So one of my students had the idea, once we stopped working in the free space project, he wanted to try something in water. He's like, what if we send data through water? Okay, great, let's try this. So we took the laser and the setup and the 1550 nanometers, and the chemists are probably laughing already, because when we sent the 1550 nanometer laser into the water, it stopped. Because water is basically like hitting a brick wall for a 1550 nanometer wavelength. And so we had to readjust our setup and find a wavelength that would go through water, because 1550 would not. And so we switched to what's called visible light communication, which is actually an interesting area of research in general. And it's still free space optics. It's still setting up, your transmitter, your receiver, but we're doing it with green and blue light as opposed to 1550 nanometer light. And these are easy to use because instead of having a huge laser system, we're just using little laser diodes for this. This is a little module that my student actually machined in the machine shop. And then this is where the laser itself is mounted in there. And you can see the green light in this case. And we transmit that through, we did it in free space to test it, but then the ultimate goal was to put it in water. So to put it in water, we got this huge PVC pipe that's about 3.7 meters long, and we set it on a lab table. We, again, set up a different circuitry. We had to build a new circuit to transmit data. So we had to find a way to get the data onto the laser diode, still 1s and 0s, not real voice. Put these 1s and 0s onto the laser, and then we transmit that data through this tube of water, get a detector over here that collects the data, and then we can analyze it to see if all the 1s and 0s that we transmitted get received. And so this is an image. My student took this picture. He thought that was cool, of the light going through the water. And so we, again, have been pretty successful. This is fairly new. We've kind of presented some parts of this research. And I think it has some practicality in submarine communication, a little better than sonar. It also has some potential from sub to satellite possibilities. So it may have some applications. The nice thing about doing research at an academic setting is that you don't have to necessarily have a purpose. You might find the purpose once you do the research. So we're still in the process of figuring out what we want to do with it and trying to establish a little better signal through the water and with the different wavelengths. So this is an ongoing project. I have to at least put a few of my students up here because they're so instrumental in everything I do. Not just in teaching, but in the research. And so I promised some of them that I'd put them up here. These were two of my student research on the free space optics project, and they were very proud standing by a poster they had presented and won first place. And this was Will, one of my great free space optics students also. He was with me when we first started the free space optics research and has gone on into the military, is doing some really good things to protect our country that he can't talk about. And then these two guys, Kevin was instrumental in starting the underwater research, the visible light communication, and Gerald, they worked together also on that. So those are my awesome student researchers. And so in summary, hopefully you learned a little bit about wave particle duality of light and some of the amazing experiments that, if you're interested in history of science, those are all good experiments to read about and learn more about. Talked about a laser and how it works. It's an acronym. A little bit about free space optics and visible light communication. So hopefully you're inspired, you learned something, and you want to go on and learn more. That's always the goal. And so thank you to Sean, thank you to the People's University, and to everybody for supporting science.
Yay, science. Can you hear me, Stacey?
I can hear you.
Oh, great. You don't have to thank me, but I'm going to do the questions now because you're not
Okay.
finished.
Oops, I'm sorry. Hold on.
Yeah, we'll just take that off. Here's the first question.
I was just trying to get rid of my PowerPoint. I'm trying to stop sharing my screen. Let's see.
Yeah, you're good.
I think
We're
I stopped. Did I stop?
Yeah.
Okay.
Question 1 from Pam. Can you see it?
Okay. When electrons are released, when light hits metal, where do they go, and what did they do? Okay, so when the electrons released in that photoelectric effect, I probably should have kept sharing. They went, in that case, through a circuit. In the photoelectric effect, they set it up so a circuit. And the reason they knew electrons were released was because current is really moving electrons. And so they had an ammeter, which detects current. And so they could see that the electrons would flow through the circuit, and they could detect that by the ammeter. So that's where they went. They went into the circuit and into the wire to flow around.
Okay.
After that, I don't know.
Here's a question for me.
Yeah, right.
Moving on.
Okay.
One said this.
Yeah, it's amazing when and that's not even one of the fastest lasers. I mean, the shortest pulses, they're getting shorter and shorter. I mean, the great thing about that is you can get so much information onto that little pulse because, as time gets bigger, as time gets smaller, frequency gets larger. So you've got a lot of space on that little pulse to put tons of information. Yeah.
Okay, here's Bonnie.
I really like some of the open resource. I know we talked about textbooks. I like textbooks. I can't think of one in general because everything I do is all textbooks, university physics books. But there are some really good in OpenStax, very basic physics that's free and online open resource. So that's always a good starting point.
Okay, here's another.
Oh, what type of program? Okay, so interesting. So we had we did a lot of LabVIEW. LabVIEW allows us to interface equipment. So all that weather equipment that you saw, we had to teach it to talk to the computer. So we did something called LabVIEW programming to interface all the equipment with the program. When we did the analysis, we used a variety of things. We used Excel, we used MATLAB, we used R. I didn't use R. Some of the others used R. So we did a variety of programming. Any language you can learn now is so valuable. Yeah.
Here's a question from a friend of ours.
It's just really fun. Why would you ever want to put a toll booth on the roof of a hospital? I don't know, but how cool is that to get a crane to lift something up and stand there? And we live in a little town, so it was the thing to do, to go watch the crane lift the toll booth on the roof.
Right. And that prompted me to ask this question.
Yeah, right.
There are more. Oh, here's another one.
Yeah, the impact of the weather on the beam is really interesting stuff. And I don't really know exactly what stops it. And we did a lot of analysis on how much the attenuation happens and what size particles affect it the most. with the fog, but we didn't really know exactly why. My speculation is if water stops it, that if the density of the fog is that thick, it's almost like the beam hitting water. And so that you get that, almost like brick wall effect for the laser light. It just can't penetrate through.
There's one from the Goober.
With the effect. So what does it say? Make a difference with the effect the sun has on the laser. Okay, so this was really interesting. My student and I, so to align this system, one person had to be in the booth on the hospital roof and the other person had to be in the greenhouse. And so to align the system, you basically FaceTime each other and you show one person in that's aligning the power meter, and then they keep adjusting until we get a maximum power. And so my student and I were doing this. It was a sunny, but it's a cloudy day. And so we had it aligned. We had it all aligned. And I said, okay, great, stop. And I would go to do something and we'd lose our power again. I said, what did you do? He said, didn't do anything. Okay, align it up again. We get it aligned, start to do something, and the power dropped. So I was really giving the student, because I thought he was screwing something up. And he said, I think it's the weather. He said, I think it's the clouds. So when the sun was out, we'd have one set up and it was working. When a cloud would come, something would happen to the beam and we would lose it. And so basically what the sun does is I think anyway, is the scintillation effect. Like on a hot day, you see that sort of rising of the heat. And so that's almost like a lensing effect to the beam. So it sort of shifts the beam a little bit. And so when we were getting the clouds and the sun, we kept getting a slight shift in the beam. If you make a bigger telescope, then it doesn't matter. If your beam shifts a little bit to one side or another, it won't matter. So that's why you see, a lot of like receivers on cell towers are pretty big. We were dealing with something really tiny. So the fact that we were able to get the signal in that tiny space makes it very, validating. If we had a great big receiver, we would never have lost our signal probably in many cases other than the fog.
Okay. Another question from Pam.
If it is interrupted, does it disappear? Well, it basically, a lot of times what happens is, think of a 1 as a peak and a 0 as nothing. What happens is, it might just start to decrease a little bit in size. So it's still there, but my ability to detect it as a 1 is no longer there. So it needs to be sort of a big separation between a 1 and a 0. So a 1 is a peak and a 0 is nothing. And so if it started getting sort of attenuated by the weather, it might get to the point where I can't distinguish between a 1 and a 0. So it's there, but it's not distinguishable with the receiver setup.
Is this a Big Bang question from Dave?
I have no idea.
I don't know.
I'm just glad people are asking questions.
Yeah, right.
That means somebody watched.
Dr. Duffy has a comment.
Yeah.
And Bonnie has a comment.
Oh, that's great. Thank you. Fun to teach, right?
Question from Aaron.
So it just depends. We have a lot of good funding within the institution. We have a really strong summer research initiative. So sometimes during the summer, we can fund students. We can apply for a little grant and they'll get like $1,500 for the summer to do research for one session. If they do 2, then they get $3,000. And they get 3 credits of 3 free like college credits for that. So they get paid and they get credit. And then we also, when I was working with the startup a little bit on the free space optics, the startup was funding also me and the students to do a lot of the research. And also, like if I write grants, we write a grant, we try to get some funding in there to get some student research help. So a multitude, and sometimes they just have to do it for free because they do it for credit, like independent study or thesis.
The Goober has another question.
So one of the goals of the company for the free space optics was to use it on cell towers for what they call that backhaul, just sending information from tower to tower. Right now, they do that with microwave a lot of time technology, which is limited to about a data rate of 300 megahertz. If we could use like the laser setup, you could do it in our case with gigahertz, but that's controlled by the data rate of the rep rate of the laser. So if you got a higher rep rate laser, then you could obviously go even faster. So it could be much better for tower to tower transfer. or even from building to building. I mean, you could use it anywhere.
Comment on Zusick I have to share.
Oh, okay.
I didn't know that either.
I didn't know that either. Yeah. Yes. Actually, Brian Greene. He was actually spoke here at VMI. It's been several years ago, but all his books are very good for explaining physics at a very nice level. Yeah, Aaron would probably know better than me.
Question.
So fortunately, well, I guess, I mean, we have to have detectors, right? So to get our data at the other side, I don't have to measure the femtoseconds. I just have to get the signal at the data rate it's coming. So the people that build a laser have to figure out all the femtosecond pieces. What I have to be able to do is have a detector that's fast enough to get the data at the 1.25 gigabits or gigahertz. And so we have to get detectors and build a receiver circuit. That's not an easy process. I just threw it up there like, oh yeah, you receive it. But there were, probably to figure out how to receive that 1.25 gigahertz signal in a lab, not out in free space. A lot of this started in a small lab on a table way before we got up to the booth on the roof.
Bonnie?
Oh, okay. So if you just type in OpenStax, Open, OPENSTAX, I think it is, you should find OpenStax and, have subjects, and you can do physics, or there's chemistry. There's a lot of them.
Geez, I didn't do that in high school. That's pretty good.
So our laser, we didn't have too much of an issue sending our laser beam through the water. We were kind of on a straight shot through that PVC pipe, and we didn't really have much of a problem receiving that at the other end. But probably the longer we go, the longer we would make that pipe, and maybe the muddier the water, it might get worse. So that's we're still in the steps of that underwater technology.
Here's a library helping out with the stacks.
Oh, there you go. They have some good stuff.
Here's Joan. Yeah, Mike's a doctor. He has his own lab.
Yeah, awesome.
Bonnie thanks you.
Okay.
Janet says, yeah, she went to a high school in Wisconsin, not West Virginia. Okay. Liam asks, here's a question from Liam, our young man who watches.
How do you make the laser stronger? Stronger, more power. So you have, depends on what's in that gain medium we talked about. So that gain medium has a big influence about how much stimulated emission you can get going in there. So your pumping source and your gain medium are really going to control most of your power that you can get out of your laser.
Yeah. When does a laser become a phaser?
Phaser, I don't know. Maser, if you switch from laser light to microwaves.
Silly question from Star Trek. Thank you. Yes, Stacey, thank you.
Thank you. It's great to have all this interaction.
You broke the record for questions tonight.
Awesome.
Yeah. Yep. People are thanking you now.
Oh, very nice. Thank you, everybody.
Up the Marie Curie. See, there it is.
Okay,
that's
awesome.
The box, folks.
Awesome.
More thanks. So, let's draw a winner, shall we?
Okay.
Drum roll, please. All right. I have the winner in my hand. Let's put that down. Here we go. The winner is Elizabeth Nank.
Great.
Elizabeth, you have won the Marie Curie tumbler. So if you'll send us your address, we'll get that mailed out to you. Stacey, wonderful presentation. Thank you very much.
Thank you, Sean.
Bringing it, to a finale for us. Yeah, Elizabeth, you won. Here she. Hey. So Tuesday is our Ann Thomas Memorial presentation from Crystal Wilkinson. Here's more kudos. Just want to share. So we're going to vote on the next People's University, so stay tuned for that. I have a couple of ideas, but I want input from the audience. And thanks everyone who attended tonight. And thank you
Thank
again.
you.
Here's from Janet. Oh, there's so many congratulations. It's hard to keep up. Okay. Thanks everyone. Bye.